Some people's personal definitions of infinity mean things like the biggest number possible, or the entirety of everything, or the universe, or God, or forever. But in math, all a number needs to be infinite is to be bigger than any finite number. So no infinite number is going to behave like one of the badly named so-called real numbers. Ugh, who decided to call them that? But an infinite number can be just barely bigger than any finite number, or it can be a whole lot bigger than that. And they don't only come in different sizes, they come in completely different flavors. In this video, all I want to do is give you an overview of the many flavors of infinity that have been discovered so far. I want to give you a feel for different infinities, like you have a feel for the halfway five-ness of 5, the even 2-ness of 2, the singularness of 1. Countable infinity is the infinity of ... It's the infinity of forever, of and so on, of adding up 1 plus 1 plus 1 plus 1 ... to get infinity, or adding a half plus a fourth plus an eighth ... to get 1. This 1 is still the result of adding infinitely, but 1 isn't a huge number. The way I see it, countable infinity isn't such a big deal either. It's just that infinite plus 1s seem more impressive than it really is. We use 1 to describe big real-world ideas all the time. 1 person, 1 hour, 1 photon, and a countably infinite amount of real-world things seems incomprehensible or impossible. But math doesn't know or care what you apply numbers to. You want to use finite numbers to represent units of time and particles and stuff? That's not infinity's problem. But countable infinity is not a number. It's a mathematical description that applies to many different infinite numbers and functions and things. Aleph null, on the other hand, is a number, a meta-number of sorts. It's the number of counting numbers. It's the first infinite cardinal number in an infinite series of infinite cardinal numbers, and it's the only countably infinite one. It's the precise number of hours in forever, the number of digits of pi. If countable infinity is a series of individual piercing lights along an infinite shoreline, Aleph null is the reflection in the water of these stabbing lights, and they wave and flow and reorder themselves to do things like make Aleph null plus 1 equal Aleph null, and Aleph null squared equals Aleph null. I mean, Aleph null is a number, and you can do numbery things to it, but it's not going to react to those numbery things the same way a badly named so-called real number would. Then there's the ordinals, ordered infinity, another kind of number entirely, where the lights can't flow and reorder themselves. They're in a swamp, and the lights congeal into puddles of infinite light. The countably infinite ordinal omega is an ordinal number with exactly as many lights as Aleph null, and all those infinite lights congeal into the same pool, and if you add a light to the beginning of the line, of course it can congeal right onto the pile, and it's still omega lights. But when you add a light in the distance, after infinite other lights, omega plus 1, the light is trapped beyond the horizon. It's stuck in order beyond the last of these infinite lights. And it can't just glom on to the light pile after the last of these infinite lights, because there is no last light. This is infinite, so it just kind of hangs out there. And so omega plus 1 is larger than omega, and larger than 1 plus omega. I mean, obviously infinite congealing swamp lights are non-commutative. There's infinite, countably infinite ordinals. And each different infinite ordinal is a different pattern of congealed light. Ordinals behave a little more like real numbers. Omega plus 1 plus 2 equals omega plus 3, but 2 plus omega plus 3 equals omega plus 3. The non-commutativity lets you play with different shapes of countable infinity without accidentally making 1 equal 2 or something. For omega plus 3 plus omega, the 3 gloms on to the second omega, and then you get omega times 2, which is different from 2 times omega, where they just meld into each other. And you can do things like omega to the omega, to the omega, to the omega ... Okay, I'm getting distracted. Anyway, ordinals are cool. There are bigger cardinal numbers, infinities that are fundamentally provably bigger than the infinity you get by counting, which are cleverly called uncountable infinities. The infinities that a ... can't even begin to approach. First, the uncountable infinity of the real numbers, smooth but individual, a dense sea of things, but any two, no matter how close, are still measurably different. They don't get stuck to each other. They can be ordered into a line, yet they cannot be lined up one by one. And the cardinality of the reals, which may or may not be Aleph-1, independent of standard axioms, can be congealed into whole new bunches of ordinal numbers. Then there's bigger transfinite cardinals, bigger boxes containing bigger infinities. In fact, there's an infinite amount of cardinals, infinite sizes of infinity, Aleph-1, Aleph-2, Aleph omega, and infinite ordinals with each of those cardinalities, omega-1s, omega-2s. I hear omega-3s are good for your brain, but if there's infinite kind of infinity, it should make you wonder, just what kind of infinity amount of infinities are there? Well, more than countable, more than uncountable. There's numbers so big, they're infinite. But the number of kinds of infinities is too big to be a number. Like, if you took all the cardinal numbers and put them in a box. You can't, because they don't fit in a box. Each greater aleph allows infinite omegas, and each greater omega provides infinite greater alphas. It's like how you can try to have a theoretical box that contains all boxes, but then it can't because the box can never contain itself. So you make a bigger box to contain it, but then that box doesn't contain itself. Just like the number of finite numbers is bigger than any finite number, the number of infinite numbers is bigger than any infinite number, and is also not a number. Or at least no one has figured out a way to make it work without breaking mathematics. But infinity isn't just about ordinals and cardinals either. There's the infinities of calculus, useful workhorses treated delicately like special cases, flaring up and dying down like virtual particles with the sole purpose of leading some finite numbers to their limits. Your everyday infinities inherent in so much of life, but that get so little credit. And there's hyperreal numbers that extend the reals to include infinitesimals, close and soft, a snowdrift of tiny numbers so near other numbers that they're almost indistinguishable. Hyperreals can describe any number system that adds in infinitesimals to the reals, which you can do to varying degrees. But the fun part is that hyperreals, unlike ordinals and cardinals, follow the ordinary rules of arithmetic, which means you can do things like division. If you divide 1 by a number that's infinitesimally close to 0, you get a number thrown wide into the infinite. And likewise, you can divide finite numbers by infinitely large numbers to get infinitely small but still non-zero numbers. The superreal numbers do similar sorts of things, but more so. Then there's the achingly beautiful surreal numbers, open, vast, stretching in all dimensions, then flowering again in newly created dimensions, filling every possible space and then unfolding into impossible space. The surreals encompass the reals, the hyperreals, the superreals, and also all the infinite infinities of the ordinals, which means the surreal numbers contain every cardinality. There is no set of all surreal numbers because there's too many to fit in a set. They're basically the most numbery numbers possible. I mean, they're provably the largest ordered field, depending on your axioms, and they still act like numbers. You can do arithmetic to them, add, subtract, multiply, divide, commutative, associative, multiplicative, and additive identities. So you can do things like infinity minus 1 and infinity divided by 2. Everything works, except dividing by 0. You can divide 1 by infinitely small numbers to get infinitely large ones, but you still can't divide by 0 without ruining everything, which is why 0 is a much weirder number than any of these infinities. But there's other sorts of infinities using other different ways of thinking about numbers. If you think of the individual numberiness of the natural counting numbers as coming from the unique number of plus ones they have in them, then defining infinity as being an infinite amount of plus ones makes sense. But each natural counting number also has a unique prime factorization. Many people think of the prime factors of a number as being what makes up its individual numberiness. There's a way in which 16 is much closer to 32 than it is to 17. Enter the supernatural numbers. The supernatural numbers are a system that decided, yep, the natural numbers get their numberiness from their unique combination of prime factors, so what if you allow infinite prime factors? In a plus 1 sort of number definition, 2 times 2 times 2 times 2 ... is the same as 7 times 7 times 7 times 7 ... But in a prime factor definition, these two infinities are fundamentally different. They feel different. Supernatural numbers can be multiplied and divided, and you can find the greatest common factor of infinite supernatural number A and infinite supernatural number B. What you can't do is add them. They don't really work unless you let go of the idea that 16 and 17 are plus 1 buddies. In fact, you can't really tell whether one infinite supernatural number is bigger than another. Sure, the supernatural numbers include the natural numbers, but in the supernatural version, the natural numbers don't belong in this +1 order. You can, however, order them all in a p-adic sort of way, which does put 16 closer to 32 than 17. It's funny because the p-adic numbers are like the most infinite-looking numbers ever. They have their digits going infinitely to the left, but this is just a notation thing. P-adic numbers are like, okay, rational numbers make sense. Now let's complete the number system to be this weird alternative to the badly named so-called real numbers. But let's face it, the badly named so-called real numbers, aside from rationals, are kinda super weird themselves. And there's tons of awesome number systems that don't contain infinite numbers, like all the types of hypercomplex numbers, though you can apply the surreal numbers to the complex numbers to get the surcomplex numbers, which seem kind of maximal if you want numbers that are commutative and associative and add and divide and stuff, so something like the ordinal quaternions would be tempting. Anyway, there's lots of infinite numbers, but those are all numbers. What about infinite space? Geometric infinities? What about the line with a point at infinity that turns it into a circle? That's a thing. Positive infinity equals negative infinity, no problem. There's only all of projective geometry, where you casually treat infinity just like any other point. And you can also divide by 0 if you really want. Yay, projective geometry! In projective geometry, parallel lines do meet at infinity. But while infinite space could refer to how big your space is in a distant sort of way, it could also refer to the number of dimensions. Infinite dimensional space is totally a thing. A Hilbert space is the name for a Euclidean space with an arbitrary number of dimensions, and it could be countably infinite dimensions or any cardinal number of dimensions. Or you could take any ordinal number and turn it into an ordinal space, which brings us to topology. Topology deals with stretching and bending things like lines and spheres and Mobius strips to figure out how they connect to themselves with no regard for distance. You can imagine taking a short line segment and stretching it into a longer one, and then stretching it infinitely to get an infinite line. Or you could take an infinitely long line and contract it down to a point. I mean, this line segment looks fundamentally smaller than an infinite line, but there's a trick. This segment has no endpoints. It's like the interval between 0 and 1, but not including 0 and 1. So if you were a point on this line and wanted to get to the very end, well, what's the last real number before 1? It's smaller than 0.9 repeating, which is equal to 1, so you can just keep going and going and going higher and higher, and you'll never get to the end, which is exactly the same thing that happens when traveling along an infinitely long line. So topology sees this line segment as exactly the same thing as an infinite line. But your usual infinite line is only the usual kind of infinite, and in topology, there is a longer kind of line, very appropriately yet confusingly called the long line. The long line is so long that you can't stretch a finite line segment to be a long line, even if you stretch it infinitely long. And likewise, the long line is not contractible. Like, here's one part of the long line, and here's another, but even if you grab them and stretch them towards each other forever, you can never get them from here to there. Infinite stretching isn't enough. So these points are part of the same line, but they kind of don't connect to each other. That's how long the long line is. I mean, it's like really long. Which is just as ridiculous and awesome and entirely mathematically provable as any of this other stuff. Finally, there's the not quite mathematical concept big omega, absolute infinity. This biggest infinity would necessarily have to contradict itself, like the box containing all boxes. But even though it's not a mathematically consistent thing, some mathematicians still believe in it, in a, I know this isn't really a thing and I can't do math to it, but it's still kind of a thing sort of way. So those are just the many different mathematical meanings of infinity that I know of, and I probably made some mistakes describing the things outside my usual areas, because these things are in such different fields of mathematics. Cardinals come from set theory, surreals come out of game theory, supernaturals come from field theory, ordinal spaces are used in topology, Hilbert spaces are used in analysis and quantum physics, infinity lets you do the projections of projective geometry, and infinitesimals let you avoid zeros in computational geometry. In fact, it's finite mathematics that's rare. Primitive recursive arithmetic, a version of arithmetic that doesn't allow infinities, can have its strength as a mathematical system quantified by applying ordinal analysis, a part part of proof theory, and PRA only has a proof theoretic ordinal omega to the omega, so that is some weak sauce. Anyway, I'm going to stop before this video becomes infinite, but let me know if you know of any other sorts of infinities, and I'll make a list, because apparently no one's done that before.